10th class students, we have finished periodic classification of elements. Now I am going to start you the chapter metallurgy. See, metallurgy mainly deals with metals, okay, but you should have an idea about non-metals also and how non-metals behaves with metals. So here I'm going to give you videos related to this chapter, principles of metallurgy, or in other terms it is simply referred as metallurgy, and sometimes you can name this chapter as metals and non-metals, okay, because metals individually they do not exist, so always they react with some type of non-metal to form oxides. Now I am going to give you the videos related to it. Do watch them. Here there are two videos which I will be repeating every week, okay, which covers the entire state syllabus of ours, okay, and my explanation will be given to you in the next week, wherein I'll be discussing all the question answers including the textbook part. So watch these videos very carefully and make sure that the digital content whatever you receive in physics of chapters, you just save them in your separate pen drive, okay students. So this is what what I want you to do is save those digital videos, so in future you will be needing these videos for quick revision. Thank you.
Hello friends, this video on metal and non-metal part 15 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 14. Enrichment of ores. So what is this? See, generally the ore which we get, right, it has mud, it has a lot of stuffs in that. Mud, stones. So before we start the chemical reaction process on this, it is good to remove this mud, stone and all. And this can be removed without any chemical process, right? So you remove the mud, you remove the stone, and your ore is enriched. It has more ores actually. And this process is called enrichment of ores. Where if you see, the ores mined from the earth usually have impurities like soil, sand, and they are called gangue. They're called gangue. These are the impurities. Impurities in the ores are called gangue. So what we do is, this has to be removed before we start the chemical process on this, right? So before we start the extraction of the metal process, we remove this, and these are removed based on the physical property. For example, sometimes you crush the ore and then use the sheave kind of thing, right, to filter it. So filter, then you can remove that, or sometimes you dissolve in water, the mud dissolves in water. So a lot of process we use which doesn't involve any chemical process. They are just physical process where we take the advantage of the physical property of the ore to remove the gangues or the impurities. So this process is called enrichment, where we remove the impurities from the ores, right? So in this, different separation techniques are applied accordingly based on the ores. So we'll not study this in deep now. Just understand that before you get the ore from the nature, it has mud, it has stone, it has sand in it, because nature composed of mud, sand, stone. So you want to remove all these things unnecessarily, because before you start the reaction of the ore is really in the oxide form. Before you start the reduction process or any other process, you want to remove these things, and removal of this process is called enrichment of ores. Once your ore is enriched, you have ores without sand or mud, you start the extraction process of the metal. Right, so the process is like this. You get ore from earth, okay, then you enrich it, remove, that is remove sand, stone, etc. Once it is enriched, you start the extraction process. For extraction process, it depends whether it is a metal of low activity series, metal of middle activity series, or metal of high activity. For all these three, we will have different extraction processes. We'll explain that. So let's take this chart which gives a clear picture of extraction. So you have this ore which have the constant. We did this enrichment first. So enrichment is done here. Enrichment is done, and we have got this step now. In this, then we have three options: high reactive, medium reactive, low reactive. Right? In case it is low reactive and you get sulfide ores. Generally with low reactives you get sulfide ores. Then you roast that metal, you get the metal and then you refine it. I'll explain this part. So in case it is low reactive, you get sulfide ores and then you do a roasting. I'll tell you what roasting is, and then you get the metals and then you further refine it. In case of medium reactive substance, you either get carbonate ores or sulfide ores, right? So in that case, what you do calcination in case of carbonate ores to convert that carbonate ore into oxide ores. In case of sulfide ores, again you do a roasting to convert into oxide ores. So the end of the day, we want to convert everything into oxide ores, right? Oxide. So when it is oxide, we just reduce this metal. So once you have oxide, you can hit in the presence of carbon, or there are various processes of reduction. We'll explain that. And then once you have the metal, you can purify it. For high reactive thing, you have to get this electrolysis of the molten. You have to heat that ore, you have to keep it in the molten form, and then use the electrolysis to get the pure metal, because that's the only option. So three options: low reactive, medium reactive, you get carbonate or sulfide ores. Then you can use this carbonate ore, you can use the calcination. Sulfide ore, you can use roasting, because the end goal is to first get the metal oxide, because metal oxide, once you have, it is the next step is simple, just reduce it and get the metal. Correct? So let me repeat this. You have sulfide ores, you do the roasting, you get the metal, you refine it for the low reactive. For medium reactive, you may get carbonate or sulfide ores. You have to convert this into oxide ores. If you have carbonate, you use calcination. If you have sulfide ores, you use roasting. You have this metal oxide, you reduce it, you purify it, that's all. And for high reactive, use electrolysis. So we'll discuss this one by one again. So let's start with the low reactive elements of metal. So if you see, these metals are very unreactive, and sometimes you get, if you have oxides of this metal, you can just heat that guy. Just by heating only, if you have oxides, metal oxide, for the low reactive, you just heat it, you get metal. We'll explain that. For example, you have HGS called cinnabar, one of the ore of mercury. When you heat in the air, it becomes HgO. When you further heat it, it becomes mercury. The reaction is like this. You have HgS, the cinnabar, heat it in the presence of oxygen, it becomes HgO, mercuric oxide, and then you again heat it, it becomes, and you get oxygen. Here you get SO2. So you just heat it and you get the metal. They are low reactive metals. Similarly for copper also, you get in CuTs form, right? You heat this CuTs, you get copper oxide, and this copper oxide, you again heat is the same with this, you get copper. So that's how it is, right? So you just have to heat it, heat, and you get the metal. And that's the thing with the low reactive metals. For the metals in the middle reactivity series, such as iron, zinc, lead, copper, etc., they are moderately reactive. Correct? And these are generally present in the carbonates or sulfides. So either carbonates or sulfides. But it is difficult to take out metal from the carbonates or sulfide ores. So we'll convert this into oxides. Correct? So what we'll do is we will convert this into oxides. So if it is sulfide, we can convert into oxide by roasting. And how to do this? You heat in the presence of oxygen. So you have this zinc sulfate. You have a lot of oxygen, because a lot of oxygen is required. You heat this guy, you get zinc oxide. And this process is called roasting, right? Roast a sulfide to oxide. It's called roasting in the presence of oxygen. Then you have carbonate ores. Carbonate ores can also be converted into oxides by heating in the presence of limited air. And this process is called calcination, because if you see, there is no oxygen required here, right? So you have zinc carbonate, you heat it, it becomes zinc oxide and carbon dioxide. Correct? So zinc carbonate is a carbonate thing, you convert this to oxide. Here also zinc sulfate, you made it to zinc oxide, because it is easy to get zinc from zinc oxide. So this process is involved if you have carbonate or sulfide, and generally for middle reactive we get carbonate or sulfide compounds also, right? So we got carbon or sulfide compounds converted to oxide using calcination or roasting. So sulfides to oxide is roasting, carbonate to oxide is calcination, right? One way to remember this is sulfide is sulfur actually, SULPHUR. So S and R are matching. So when you have sulfur, you use roasting. And carbonate and calcination both starts with C actually. So if it is carbonate, we'll use calcination. So that's easy to remember. But for sulfide, it is roasting. Why? Because sulfur is R ends with, sulfur ends with R. So sulfur is roasting and carbonate is calcination because both are C. Now once I have the oxide form, it can be reduced the corresponding metals by using reducing agent. And reducing agent, one of the example is carbon, right? Because when zinc oxide is heated with carbon, it gives zinc. You have zinc oxide, when you heat with carbon, you get zinc. And carbon is very cheap, right? So you heat zinc oxide or any metal oxide with a reducing agent like carbon, you get carbon monoxide and zinc. But we can't use carbon everywhere. For some reactive metals, we can't use carbon. So in that case, we use displacement reaction. If you see, sometimes displacement reaction is used, and for example, sodium, calcium, aluminum, etc. are used as reducing agent in this case. Sometimes when you can't use carbon, in that case we use sodium, calcium, and for example, manganese, you have manganese oxide, you can't use carbon, so in that case we'll use aluminum. So you get manganese out and Al2O3, and you get heat also. Correct? Sometimes we can't use these directly. And please note that these displacement reactions are highly exothermic. The amount of heat is evolved is so high that the metal produces in the molten state. It's very exothermic. Heat is very high. Now we'll discuss a new type of reaction called Thermit reaction. So reaction of iron oxide with aluminium to join railway tracks generally is used called Thermit reaction. They are used to join metals. They are used to join metal parts. The reaction is this: you have iron oxide, you have aluminium, you get iron and Al2O3 and heat. It generates heat actually, and this melts the metal and clean the metal is joined. This reaction is called Thermit reaction, a very common reaction to join the metal parts. Reaction name is Thermit reaction. So in this case, if you see, these metals are very reactive. On the top of the activity C, they are very reactive, right? And they cannot be obtained by heating with carbon. Why? Because if you see, carbon will not be able to reduce the oxides of sodium, manganese and calcium. Carbon will not be able to, right? Why? Because these metals have more affinity towards oxygen than carbon. So that's why we can't use carbon. We can't use this carbon. We can't use this carbon for these metals, right? So that's why we use electrolytic reduction. Electrolytic reduction. In this case, for example, sodium, magnesium and calcium can be obtained by electrolytic reduction of their molten chlorides. For example, you have this sodium chloride molten form, and then in this case you use electrolytic reduction. The metals will be deposited at cathode and chlorine will be deposited at anode. I'll show you how. Example, if you see at cathode, you have this guy, right? So you have this cathode here, let's suppose, which is negative charge, and you have anode here, which gives a positive charge. That means there are very lot of electrons, free electrons here, right? Because cathode will give negative charge, so a lot of free electrons will come here. So this guy is an NaCl solution. Let's suppose NaCl solution, sodium chloride. So NaCl will be in this form, Na plus Cl minus, Na plus Cl minus, like this. So since it is Na plus, it will be attracted towards this electrons, correct? Because there are so many electrons. This is a negative charge, this is positive, it will be attracted. Negative and positive attracts, right? This guy attracted. And chlorine will be attracted towards this side, this positive charge, right? Sorry, this guy positive. So if you see, what happens is, end of the day, I have my this cathode, and I have my this anode. So all my chlorine ions will come here, and all my sodium will. So now what happens is, the sodium plus from NaCl will get an electron from this guy. It will become sodium and will get deposited here, right? And at anode, this guy chlorine minus will get this, will lose one electron to this guy, because you see the electron flows like this, right? Electrons flow like this. So lose one electron and it will become chlorine gas and it will get deposited here. You understand the logic? What's happening here? So we have this container and we have some solution here, which is the nothing but sodium chloride, molten sodium chloride, and molten sodium chloride is NaCl molten, which has Na plus and Cl minus. So Na plus will get attracted toward this electron, that is negative side, and Cl minus will get attracted toward the positive side, and all this chlorine gas will get in this part, that is the anode part, and all this sodium will get in this part, that is cathode part, and that's how this extraction happens. Correct. So once I have my metal extracted using the various processes described, I have to refine these metals, right? Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again. Hello friends, this video on metal and non-metal part 16 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 15. So let's do the refining of the metals. As I told, the metals which we get are not pure, right? They have impurities, and the method that is used to refine the metal is electrolytic refining. We'll explain this, what is this electrolytic refining, but this is the one that is used to refine the metals. We'll explain the electrolytic refining method. So if you see, many metals like copper, zinc, and this are refined electrolytically. We'll tell you how. In this process, a impure metal is made anode. So if you see, this is anode, this is cathode, right? So this guy is my impure, and this guy is pure. So I'm assuming it's a copper, right? Impure metal is impure copper, which has impurities in it, and this is a pure. This is very thin strip of metal, very thin, and this is actually thick. This is thick. I should have made this guy bigger actually. It's okay. So there's a very thin strip of pure and very thick strip of impure metal. Pure at cathode and impure at anode. And then a solution is used of metal salts. This is copper, so I'll use copper sulfate. So I'll use copper sulfate, CuSO4. Right? So this is a copper sulfate solution in this. Is used as electrolyte. On passing the electricity, the pure metal from anode dissolves into electrolyte, and then it goes to the copper, right? And also the equivalent amount of metal goes to this copper, and the impurities settle down. I'll explain how it is done. So if you see, this guy has copper, so the moment I have my copper sulfate solution, it will have copper plus ion, correct? So copper plus ion, this guy have more copper plus ion, this guy will have. So since it is a copper sulfate solution, it will have a lot of copper ions. Now what will happen is, see, if you see, the flow of electron is in this direction, right? This is the direction of flow of electron. So here electrons will be there. So it will have electrons here, electrons here. So this copper from copper sulfate ion will join this guy. It will become copper. Copper plus an electron will become copper, and it will add to this thing. So it will add to this. So more and more copper will add to this, right? Because also in this I have copper. Copper wants to lose electron, right? So, and flow of electron is in this direction. So copper will lose electron in this and becomes copper plus, and will go to the solution. And the mud and all the mud impurities will be here. It will go down because that mud will not become copper plus, right? So if you see, the mud and other elements will fall down, and the copper thing, when it lose electron, the electron flows now from here, right? Electron flows from here. Copper plus will be part of the copper sulfate solution, and from here, now we have more copper in this copper sulfate solution. Since we have more copper in the copper sulfate solution, we have this electrons here in this cathode, this free electrons. The copper will get attracted toward this free electrons, right? It's the negative, it's a positive, and then it will merge with the free electron and deposit it in this copper plate. So gradually what will happen is, gradually if you see, this will get over. This will not be there. This will get diminished, and this guy will get more copper like this. It will get thicker, it will get thicker, it will get thicker, it will get more and copper, and this guy will get diminished. This guy will get diminished completely, right? So this guy will get thicker. What is happening is the copper in this is losing an electron, because the electron is flowing from here, right? Is losing electron to become copper plus ion, and the guy is going in the copper sulfate solution, right? This is becoming part of copper sulfate solution, and then this copper plus is getting attracted to what is negative side, right? Because there is free electrons here, and then it merges with the negative electrons to become copper. Correct? Now is the question time. Define the term gangue, mineral, and ore. As we have told that mineral is nothing but a national state. In national state you get metals, right? And they get in combined state also. Ore is a subset of minerals from where you can extract the metals profitably, and gangue is the impurities in the ore. Correct? So it is like this. You have this mineral. Some of the mineral is ore, and inside the ore you have gangue actually. So inside ore contains gangue, and some of the minerals are ore. Not all the minerals are ores. Name two metals which are found in free state. So we know that gold, silver, and platinum, these are found in free state in the nature. What is the chemical process is used in obtaining a metal from its oxide? So we use reduction. Reduction is used to obtain metal from its oxide. So sometimes carbon is used as reducing agent. Sometimes other metals are used. In that case we use displacement reaction. And sometimes we used it is achieved the oxidation. I mean, from oxide we get the metal from electrolysis. I mean, using electrolysis we get this metal. So for the first case, for example, I have zinc oxide. You add carbon to it, right? And you reduce, carbon is used as reducing agent here. You get zinc plus carbon monoxide. This is the metal you have got. This is the first case. Second case, we use displacement reaction. For example, you have MnO2. You react with aluminum. You get Mn plus Al2O3 plus hydrogen. Sorry, heat you get. So we can balance this. We can make it Al2O3. We can make it 4, 3, and 2, 3. This is a balanced reaction. The third case, I use electrolysis, where I use this electric current and break that oxygen get deposited somewhere else, and my metal gets deposited somewhere else, right? Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again. Hello friends, this video on metal and non-metal part 17 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 16. Now we'll start with a new topic called corrosion. What is corrosion? So when iron is exposed to a moist air for a long time, it gets this brown flaky substance, right? This guy is called rust, and this process is called corrosion. So what happens in corrosion? If you see iron, it reacts with oxygen. It gives Fe2O3. Correct? You can balance this. So this becomes 2Fe and 3 by 2. Yeah, this is the Fe2O3 is the reaction. Correct? So this is nothing but my corrosion reaction. This guy is rust actually. This guy is rust. And this is a very painful thing, because a lot of time we buy something and it gets corroded and it's waste. The strength of this article is gone, it's weak, you can't use it anymore, it looks dirty, it looks dingy actually. So this is something which you don't want, right? This is something which is unwanted thing, and we always want to avoid corrosion. So let's see what we can do on that. So what is required for corrosion? So we know that both air and water is required for the corrosion. Correct. So to prove this, what we can do is we can take 3 test tubes. In this test tube, we have put this nail, and this nail is exposed to both air plus water, right? Because there's a air, there's a water. This guy is put in distilled water, and you have put this oil layer, so that there is no air that comes to this water or comes to this nail. So that here we have water but no air, right? Here in this case we have put calcium chloride, and this is dehydrating agent actually. It will remove the water, it will absorb all the moisture actually. So here we have air but no water. Why? Because all the moisture in the air is absorbed by this guy, dehydrating agent actually. Okay. So what we'll see that we'll keep this for 2 or 3 days. We'll see that this guy got rusted. This guy got rusted. This guy got no rust. This is also no rust. So in this case we provided water but still there was no rust. In this case we provided air but there was no rust. In this case we gave air and water both and it rusted. Thus we conclude that both air and water are required for this corrosion. This is an experiment you can do in your home also. You can have these 3 test tubes, put this in water, right, and it will have this air also. So this has air, water both. Put this in water, put the oil thing, so that there is no extra air inside that. This has only water. Put this some calcium chloride you can get from lab, and put this in the test tube, close all, and after 1 week or something you'll find that this gets corroded and this are all fine. So that's the message we have got, and the key we have got, that both air and water is required for corrosion. So we can stop one of these, we can stop corrosion, right? So we can stop corrosion by painting, oiling, greasing, galvanizing, chrome plating, anodizing, making alloy. So painting, we know with painting, the layer of paint and water and air both are avoided, so there is no rusting. In oiling also we have a layer of oil and there is a air avoided, right? So you can avoid this. Greasing also does the same thing, right? So you can avoid this water and air. These all things we know. Galvanizing is something which is new to us. We'll learn this. Chrome plating is plating a layer of chrome. Anodizing is also new to us. Making alloy is also new to us. So we'll learn all these actually, right? What is galvanizing, chrome plating, anodizing, making alloy, and how these things help in preventing corrosion. So first thing is galvanization. Galvanization is the method of protecting steel and iron from rusting by coating them with a thin layer of zinc. And I'll tell you, it's a very critical thing. Why we coat with the layer of zinc? Why don't we do with the paint? We can coat anything with the paint also, but something like utensils, if you coat with paint, the moment you heat it for cooking something, the paint will burn, glow off. So we can't coat with paint in such scenarios, right? So we have to use something else. So in that case we use this zinc, and this process is called galvanization, correct? So, and zinc here acts as a anode so that it cathodically protects steel. That means even if a steel is scratched or broken, the zinc part is scratched or broken, it will still prevent. The zinc will still prevent, because zinc will act as anode. It will still prevent. Let's explain this why. So the method of galvanization is like this. We have 2 methods. One is hot dip galvanization. The other is electroplating. See, I'll tell you how this sacrificial thing works. So if you see Fe, when reacts with oxygen, becomes Fe2O3. So gradually what is happening is Fe is becoming positive, right? So iron is losing electron for corrosion, correct? And when it is losing electron, it is mixing with oxygen. So what this guy is doing, zinc is acting as anode. Anode is something which takes electron, right? So whatever extra electron it has given, this zinc will take it. Zinc will take it, and it won't allow iron to get rusted, correct? Because anode takes electron. So zinc will take electron and it won't allow iron to rust. Correct? See, iron has a tendency to lose electron. So iron will lose electron anyway, right? Now, if this electron is taken by oxygen, it rusts. If this guy is taken by zinc, it won't rust. That is happening here. So the moment this extra electron which iron has loose is taken by oxygen, there is a rusting that gets Fe2O3. But the extra electron, whenever it comes, zinc takes it, then oxygen won't be able to take it, right? If zinc takes it, then that means Fe2O3 is not formed, and that's how it prevents rusting. Hope you understand this. The sacrificial anode, you can say, where zinc will take the extra electron. Zinc will not allow oxygen to take the extra electron. Correct? Now let's go and do understand these two methods: hot dip galvanizing and electroplating. So in hot dip galvanizing, what we do is we have this zinc, molten zinc. In this we dip aluminum. It's called hot dip galvanizing. In electroplating, what we do, we have this, I think we have discussed electroplating thing, where we have this aluminum here and where we have this zinc thing here, right? We have this zinc thing here. So it goes here gradually. So in this case, this is aluminum and this is made the cathode actually. And you have some anode and you put some battery in this, right? So what happened is this has some zinc solution actually. Suppose it has zinc ion in zinc sulfate form. Zinc sulfate, this guy has a negative electrons. It gets attracted and it forms a layer here. So if you see, this guy gets a zinc layer. Correct? Hope you understand this. You have this beaker. In this you have molten zinc sulfate solution, and then you pass the electricity, right? And this you get electrons here, electrons, and you have this zinc ions here, zinc ions, sulfate ions here. This zinc ion is attracted towards this electron, and this it gets it gets a layer of this. The zinc ion will get this electron and will become zinc and will get deposited here. Correct? Now let's see the third process called alloying. Alloy is a homogeneous mixture of two or more metals, or a metal or a non-metal. Please note, alloy is a homogeneous mixture of two or more metal or a metal and non-metal. So you can have a metal non-metal combination, or you can have n number of metals combination also. Like you have metal plus metal combination this way, or metal plus non-metal combination. So this is alloy, right? It is prepared generally by first melting the primary metal and then dissolving other metals in a different proportion and then cool down. For example, I'll take some examples here. So for example, iron is very soft, right? And it stretches easily when it's hot. But when this guy is mixed with this guy, 0.5% or 0.05% of carbon, it becomes very hard and strong. And that is what we call alloying. So you have this, you take 99.95% of iron and 0.05% of carbon. You mix it in the molten state, cool it down, this becomes very hard. And alloying is a very good method of improving the property of metal. There has to be a reason why we are doing alloying, right? So it improves the property of the metal. For example, in this case, iron was a little soft element when hot. Then what we have done is we have put only 0.05% of carbon and it has become very hard and strong. Another example is when iron is mixed with nickel and cadmium, it becomes stainless steel. It doesn't rust. The rusting problem is solved just by adding nickel and chromium in a small quantity. Right? So that's what the alloying is. The beauty of alloy is you add a metal the bigger portion has to be this big metal, and then add small portion of some other metals in the molten state, right? Everything is molten, and then you cool it down. The cooled down metal you get is alloy, and it has very good properties. For example, steel has iron and small amount nickel and chromium. With this, there is no rust. The rusting problem is solved. Iron is soft. You add 0.05% carbon. It's very hard and strong. That's what the beauty of alloy is. You add small amount of other metals or non-metals to it, and the property change. One more example can be this pure gold. So if you see, gold is 24 karat, and that's very soft. You can't even make ornaments out of that. If you make, you can break it with the hand also. So what we'll do is, they generally add copper or silver to it and make it 22 karat. That is, they are adding impurities to it to make it 22 karat, and then the gold is strong. The gold is strong, and you can make ornaments. Correct? So we have a new term called amalgam. What is amalgam? So if an alloy has mercury in it, it is called amalgam. So if you put even 1% of mercury, that alloy is called amalgam. So just a term we should know. So I just have put this. Now, conductivity of alloy is generally less than pure metal. Just please note, it is generally less than pure metal. Correct? So if we talk about conductivity and melting point both, conductivity and melting point both of an alloy is less than pure metal. For example, if you see the brass is the alloy of copper and zinc. Bronze is the alloy of copper and tin. They are not so good conductor, but copper is a good conductor. So in copper you add small amount of zinc, it becomes brass. Copper you add small amount of tin, it becomes bronze. They are not very good conductor of electricity as compared to copper. Also, we talk about the melting points. If you see solders as the alloy of lead and tin, it has a very low melting point, and that's why you use for soldering, right? It melts easily. It has very low melting point as compared to lead and tin. So that's why the alloy generally has low melting point and it has low conductivity as compared to the pure metals. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again. Hello friends, this video on metal and non-metal part 18 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 17. So the question says the metallic oxide of zinc, manganese and copper are heated in the following with the following metals. Which of this will have a displacement reaction? So we know that manganese is stronger than zinc, is stronger than copper. This we know because we have manganese, zinc and copper involved. So this series we know, right? So zinc will not react with zinc oxide, manganese oxide will not react with manganese, and copper oxide will not react with copper. This we can directly cut, right? Now when you talk about zinc, will zinc react with zinc displace manganese oxide? No. Why? Because zinc is weaker than manganese oxide. Will zinc displace copper? Yes. So it will displace copper from copper oxide. Magnesium. Will magnesium displace zinc oxide? Yes, it can, right? Because magnesium is stronger than copper. Will magnesium displace copper? Yes, magnesium can displace because magnesium is stronger than copper. Will copper displace zinc? Copper is weaker than zinc. No. Will copper displace magnesium? No. So this is my solution. Very simple. You just need to know the reactivity order. Which metal do not corrode easily? Answer is gold. Gold doesn't corrode. You know that? It's very less reactive. Which of the following pair will give you displacement reactions? I have NaCl solution and copper metal. So in this case, if you see, my copper is more reactive than silver. We know that. So copper will displace silver from this. This is true. Silver is less reactive than iron, so it won't do. Aluminium is less reactive than magnesium, it won't replace. Copper is less reactive than sodium, it won't replace. So in this case, the only solution is this guy. Why? Because copper is more reactive than silver. Okay. Let's take another question. An element reacts with oxygen to give a compound which is a high melting point. This compound is insoluble in water. The element is likely to be calcium, carbon, silicon, iron. So we know that so in this case the answer has to be calcium, because calcium when react with oxygen to form a compound which is high melting point. Iron is gives rust. Silicon, carbon, don't know much. Calcium is the one that is the answer. Food cans are coated with tin, not zinc. Why? Because they've given 4 options. Zinc is costly than tin. Zinc has a higher melting point than tin. Zinc is more reactive than tin, and zinc is less reactive than tin. The answer is obviously zinc is more reactive than tin. That's why it is coated with tin, not zinc, right? So this is the answer. Why? Since tin is less reactive and zinc is more reactive, so it is coated with tin, not zinc. Correct? Since zinc is more reactive, it is not coated with zinc. Tin is less reactive, it is coated with tin. You are given a hammer, a bulb, battery, wire and switch. How will you use them to distinguish between the samples of metals and non-metals? So if you see here, with hammer we can use this ductility or malleability property, right? We can just beat it. So we'll beat that particular sample, right? If it is malleable, I can say that it is metal. That is one thing. The second thing, bulb, wire, switch. With this I can check for electrical conductivity. So I have some metal like this. I can put this metal like this. I'll put a battery, right? I'll put a bulb. This wire is there and there's a switch, right? So with this I can check whether this particular metal or this particular sample will conduct or not. So if it glows, that means it's a metal, right? Because metal are good conductor of electricity. So with this 2 property, malleability and electrical conductivity, I can tell whether the sample is metal or not. Correct? Because the first hammer I'll use for malleability, and battery, bulb, wire and switch I'll use for electrical conductivity. Correct? What are amphoteric oxides? Give 2 example of amphoteric oxides. Amphoteric oxides are oxides which are both acidic and basic. Right? For example, Al2O3 is one and zinc oxide is one. They are all amphoteric oxide because they are both acidic and basic. Name 2 metals which will displace hydrogen from dilute acid and 2 which will not. So you can see the reactive metals like sodium, potassium, they will displace hydrogen from HCl. And weak metals, for example, you can say that gold, copper, right, silver, this will not displace. This will not displace. Correct? So my strong metals will displace and weak metals will not displace. Correct? The next question says that in an electrolytic refining of a metal, what would you take as anode, cathode and electrolyte? So we know that anode we generally take as impure substance. We take cathode as thin strip of pure metal. We have done for the case of copper, actually we have shown that. And my electrolyte solution is nothing but my metal solution. For example, in case of copper we take copper sulfate, right? So why do you like this? Because in case of cathode, if you see, cathode will give this is cathode, which gives a negative charge, right? It's anode with a positive charge. So cathode will give a lot of electrons, and with this electrons, let's suppose copper is my thing, copper sulfate, from copper ions from copper sulfate will dissolve here, and this guy will give a positive charge, so which will help in dissolving copper from this impure copper to copper sulfate solution. That's why we use cathode for, in cathode we use thin strip of pure metal, and anode we use impure metal, and this solution we use is metal solution. Correct. So the question is, what type of oxides are formed when non-metals combine with oxygen? Please know it's non-metal. So generally we get either acidic or neutral. So if you have, let's suppose, sulfur, you add with this, you get SO2, this is acidic. You have carbon, you add with this oxygen, you get CO2. So this guy is neutral and this guy is acidic, right? So you either get acidic or neutral oxides when you combine non-metal with oxygen. You have to give reason. First, platinum, gold and silver is used for making jewelry. So for this, the reason is, for this I'll give the reason as, I'll say that they are less reactive. Gold, because they are less reactive, it can use for jewelry. They are corrosion free. They don't corrode. They are malleable, so we can make a jewelry. And they have shine. Since they have shine, they are used to make jewelry. All these reasons I can give. Potassium, lithium and sodium stored under oil, they are very reactive. They are very reactive, and the moment it comes to moist, that is H2 in water or air, it reacts. So that is kept in oil. Aluminium is highly reactive metal, yet is used for cooking utensils. That is because we know that aluminium forms oxide Al2O3, right? Aluminium oxide, and this guy is non-reactive. This guy is non-reactive. It is resistant to corrosion. This is non-reactive. I'm talking about aluminium oxide, and aluminium as such is lightweight, right? It is cheap also. It's not very costly, and it is good conductor. That is most important thing, because when you are making a utensil, it has to be good conductor of heat. It has to be, so aluminium is good conductor of heat. The next question is, you must have seen the tarnished copper vessels cleaned with lemons or tamarind juice. Why? Why are the source substance used for cleaning the vessels? I know the source substances are acidic in nature, right? So if you see this guy lemon has citric acid. So if you see this copper actually reacts with carbon, it gets CuCO3. Right? When you heat copper, when you use copper a lot, this becomes CuCO3. This is green color, right? This green layer. To remove this, what we use this guy is basic, right? So with this base, I used acid, that is any of this lemon or tamarind, to neutralize this effect and remove this CuCO3. It dissolves this layer. This is the layer, and this layer is dissolved with the acid, correct? Because CuCO3 is a basic layer and dissolves with the acid. A man went to a door-to-door posing a goldsmith. He promised to bring back the glitter of the gold of the old ornaments. A lady gave the old bangles, dipped in the particular solution. The bangles sparkled like a new, but the weight reduced drastically. Lady was upset, but before the argument, this guy ran away. So you want to know what was the solution? We know this. This is a easy one. This was aqua regia. This is 3:1, where I have HCl and HNO3 nitric acid concentrated. We have concentrated HCl nitric acid in 3:1 in fresh prepared, and that is aqua regia. And gold dissolved in this. Gold doesn't dissolve in HCl. Gold doesn't dissolve in nitric acid, but in this aqua regia it dissolves. So that particular solution is aqua regia. Give reason why copper is used to make hot water tanks, not steel. I mean, we don't use iron to make hot water tank. If you see the geysers which you have in homes, the hot water geysers, there copper is used. Iron is not used. Why? Because if you see copper and if you see water, if you pass heat also, if you make it warm also, there is no reaction. there is no reaction, right? But if you take iron, but when you take iron, if you see iron and you react with water, you get Fe3O4 plus H2, right? So I mean, if you balance this becomes this, and you need heat. So if you see, iron reacts with hot water. Copper doesn't react with hot water. And that's why copper is used for making hot water tanks, not the iron. Let's do a recap of what we have learned. Elements can be classified as metals and non-metals, right? You have metals and non-metals. Metals are lustrous, malleable, ductile, good conductor of heat and electricity. They are solids except mercury. Metals, they lose electrons to non-metals. Metals combine with oxygen to form basic oxide. Example, aluminum oxide, zinc oxide. Are example of oxides which show both acidic and basic, and they are called amphoteric oxide. They are exceptions actually, right? And then different metals react with water and acid in a different form, and that's because of the different reactivities they have. And the list of common metals can be arranged in their order of reactivity. That's known as activity series. We have done that using experiments. Metals above hydrogen in the activity series can displace hydrogen from dilute acid. So in the activity series we have hydrogen also. So metals above hydrogen can displace hydrogen from the acid. More reactive metal will displace a less reactive metal from its solution. Metal occurs as a free element or in the form of compound also in the nature. The extraction of the metal from the ore and the refining, the whole thing is called metallurgy. It's a very old process. People have been doing this since long. Alloy is nothing but a homogeneous mixture of two or more metals or metal or non-metals. It has different properties. The surface of some metals such as iron is corroded when they are exposed to moist air for a long time, and this phenomenon is called corrosion. Non-metals have the property exactly opposite of metals. They are neither malleable nor ductile. They are bad conductors of heat except graphite, which is good conductor. And thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.